Yeah, good number. 15 have joined.
Yes, sir. Yes, sir.
I have forwarded to old IRP or some group was there. I forwarded there also.
Ria, this YouTube, there is a one green color button in the top that shows live and streaming. Is it started or?
If you go to the YouTube video segment, it's showing our discussions also, but in a recorded mode. So I think as we go on, it may record and show not
I think
exactly
that
the
must
same.
be the way. That must be the way it works.
Yeah,
Okay.
you can go to YouTube and check the videos. It can show our discussion.
Okay, then we
So
start.
it has.
Okay. Ria, shall we start? Your
Do the participants need a password to get into the YouTube channel?
no, that is open actually. And Zoom anyway, we have supplied that.
Yes, sir, we can continue now.
Okay. Thank you. Good evening, Dr. Sunil, for immediately accepting our invitation to give you a talk on this special topic. Actually, this is on what is called accelerator specific topic, but again, it is more into the advanced system, that is advanced photon source actually. And a brief introduction will be given by Ms. Ria, following a small brief note from me. Specifically, this IRP Young Generation Network was formed during this AOCRP6, and their intention is to bring more and more people together through this lecture series and meetings during this conference and all. This is the initiative, and this lecture is the third one actually. After Dr. Thierry, then Dr. Haridasan, and then third one is by Dr. Sunil. So every month we are inviting eminent personality from this area of radiation protection, and this really is a good uh, information and knowledge sharing a platform, and it is again recorded and kept in the YouTube channel of IRP for future use for other researchers in this field. So, without further elaboration, I request Ms. Riyade to briefly introduce the speaker, and then we'll hand over the platform to Dr. Sunil for this lecture. Thank you, and good morning, everyone. And our speaker is 12 hours behind us. Now it's night at US, maybe 9:30, 10 o'clock. And again, I thank Dr. Sunil to accept and delivering this, going to be this wonderful lecture. Thank you, Dr. Sunil.
Thank you, sir. Let me just introduce our today's guest of lecture. Dr. Sunil C. is the radiation physicist at the Argonne National Laboratory since 2019, handling radiation protection calculations for the various accelerators. Prior to joining Argonne, he was a radiation physicist at the National Synchrotron Light Source 2 at the Brookhaven National Laboratory in New York, a scientific associate with the Compact Muon Solenoid CMS detector at CERN, Switzerland, with the added role of group leader of the radiation simulation group of CMS and a scientific officer in the Accelerated Radiation Safety Section of Health Physics Division BARC. He is from the third batch of Health Physics Training Program of BARC. He has a PhD in physics from Mumbai University and is an associate editor of the Health Physics Journal. He has several publications in the field of accelerated radiation protection. He is also a member of CERN Fluka Collaboration and PHITS North America Consortium. The floor is yours, sir.
Thank you, Ria. I'll need your help as I share my screen just to make sure that you're seeing the right screen. Give me a minute. I'm going to put this in presentation mode. Let me know what you see.
It's in the presentation mode, sir.
You're seeing the right one, right?
Yeah.
Okay. Let me minimize the screen here so that I can see. All right. Thank you for the introduction and thank you for the invitation to this to give this talk. It's been after a long hiatus. I'm glad to be back amongst known people, known colleagues, ex-colleagues, unfortunately. And it's been I'm really happy to showcase some of the work that I've been doing in the past 5 years at the Argonne National Laboratory. At the outset, I would like to apologize. I think there's a small error in the abstract that I submitted. There, I mentioned something about the radioactive ion beam source. Unfortunately, I don't think I will have the time to talk about that. But I'll be talking about the advanced photon source. There's enough material in that itself, to cover more than an hour of talk. So I will explain the radiation physics and radiation protection aspects as practiced in Argonne National Lab specifically, but in general at the various DOE labs. Just our customary acknowledgements, some of my colleagues and the Office of Basic Science that actually promotes the Argonne National Lab through its official grants and some of the computing clusters that I use in Argonne for my computational work. Of course, goes without saying that I also acknowledge many of my mentors early days from BRC, where I learned the trade. Particularly Dr. P.K. Sarkar, K.N. Kirti, and of course Haridas as well. Argonne is situated about 45 kilometers southwest of Chicago City. It's a federally funded DOE National Lab under the Office of Basic Science. It's engaged in multidisciplinary research in engineering and science research. It was established in 1946, and there are no reactors on site, but Argonne has a rich history in that field, starting from, we all know about the Chicago Pulse, but also lesser known fields such as nuclear submarine developments, experimental boiling water reactors. That was the first one, probably was in Argonne, and several breeder reactors with the plutonium core. It's a campus map that shows the various facilities. Particle accelerators in Argonne, the major one, of course, is the advanced photon source, which is it's now a fourth generation light source. We also have what is known as an argon tandem LINAC accelerator. It's a heavy ion accelerator capable of accelerating up to like 10-20 MeV per nucleon. It's something similar to the Pelletron at TIFR or the Pelletron at Nuclear Science Center in Delhi. There is no tandem accelerator. It's pretty much RFQs, low beta section and superconducting cavities with an ion source of ECRs. So I think there are a couple of ECRs. We have a Wakefield accelerator, which is not open to users. The APS and the Atlas are open to the user community. And then we have like a 60 MeV high current electron accelerator, which produces medical isotopes. There's a small Venn diagraph generating electron accelerator again, and a couple of neutron generators on site. It's also, there's a history on accelerators as well for argon. There was a 12 GeV zero gradient proton synchrotron, which was operational here in the 70s. It actually accelerated the first high energy polarized proton beam. There was also an intense pulsed neutron source facility based on a proton spallation reaction. Now, radiation protection in argon, argon is first of all operated by a contractor, which is how DOE operates all their national labs. The contractor that is operating argon is called University of Chicago Argon LLC. U Chicago also operates Fermilab, for example, which is also very close by to this location. So the radiation protection aspects in all DOE labs is governed by what is known as a Title 10 of the Code of Federal Regulations, Part 835, in short, 10 CFR 835. It requires all DOE labs to manage and administer radiation protection programs, set standards for internal and external exposure, monitor individuals, keep records, ensure that entries to various radiation areas are controlled in an adequate manner, impart radiation safety training, ALARA compliances, and the whole 9 yards. 10 CFR 835 is not only the Code of Federal Regulations. We also are covered under 10 CFR 830, which is for nuclear safety management, if we have facilities in that category. And there are several DOE orders which talks about accelerator safety and radiation protection for the public and the environment. So the way the CFR 10 CFR 835 is implemented is through obviously of the lab management through the director of the lab and ESH director, but also through the radiation protection program director. So we have a radiation protection program document, which is a high-level document, which is what is approved by the DOE. It's detailed in the radiological safety program description, which has got spin-offs in various lab procedures. The RSPD also has it forks into various health physics procedures, policies, technical basis documents. It also identifies qualifications required for technicians and the trainings and things like that. When necessary, we also rely on some of the ANSI standards and the other DOE guidelines as and when required. The advanced photon source is first started operating in 1996. In April of 2023, we shut down the facility for the upgrade. The tunnel and the only thing that was upgraded was the storage ring. The electron starts, the LINAC accelerates to about 450, 500 MeV. It goes through what is known as a particle accumulator ring, which is essentially, it doesn't accelerate anything. It just compresses the bunches into high charge states, which is then accelerated in the let me get my laser pointer. And which actually it gets accelerated in the booster synchrotron. It enters it accelerates up to 6 GeV, which is then injected into the storage ring. Sectors, it's divided into 40 sectors. Sectors 1 to 35 can accommodate beam lines. Sector 36 to 40 is mainly for the injection area of the machine. Each sector can accommodate 2 beam lines. One is a bending magnet beam line and an insertion device beam line. And it's the circumference of the ring is about 1.1 kilometers. So for the upgrade, the APS, the last light from the old APS was somewhere in April of 2023. The commitment to DOE was that the users will get the new synchrotron light in April of 2024. That means within a year, they were supposed to completely remove the storage ring and install and then produce the first light. And in fact, they accomplished that with much earlier than the date that they set for themselves. This was done through extreme planning. They assembled all the girders and magnets in a off-site warehouse, brought them in trucks, and then assembled them like Lego toys. And that's how they managed to do that upgrade in a very short time. If you go from essentially the transition is APS was a 7 GeV 100 milliamps machine. It reduced to 6 GeV, but the increase in stored current of 200 milliamps. This all thing was actually to reduce to get a much tighter synchrotron radiation beam profile. You can see from here, which is 3,100 picometer radians to 42 picometer radians. It's about a factor of 100 reduction in the beam size in the horizontal plane, which increases the brightness of so many photons per area per radian square and things like that. The old machine was what is known as a double bend achromatic lattice. The new machine is what is known as a multi-bend achromatic lattice. As you can see, it's the longitudinal gradient dipoles were the bending sources for the previous machine. You have got much more number of magnets, and the idea is to turn them electrons slowly so that the emittance is much lower compared to the previous machines. The MBA lattice APS is not the first machine to use the MBA lattice. That was Max 4 in Sweden. That was followed by ESRF in France, which is also a 6 GeV machine. And then there's Sirius in Brazil. There's one in China. But APS is the first machine to introduce what is known as a reverse bend in the lattice. So typically the electrons bend only in one direction. That is, trying to go around in that circumference. But we have what is known as a transverse gradient dipoles. I'll show that in a minute, which actually kicks the electrons outward also and then brings it back, all in the quest to get a much smaller emittance of the beam. So here's an MBA lattice, at least one section of it. So these are the longitudinal gradient dipoles, and what you see here is actually a transverse gradient dipole. Essentially, it is a quadrupole in the sense it has got both actions. There are 4 poles, so it serves 2 functions. One is to focus like a quadrupole, but also it bends the electrons in a dipole fashion. There's some kind of an offset kind of a quadrupole. And then, of course, the insertion devices can be, for example, it's an undulator. It can be either as an inline undulator. I don't know if this is an inline or not, but it looks like a canted one. But also you can have what is known as a canted structure, like, with which its beam diverging by like a few milliradians, essentially giving 2 arms of synchrotron radiation beam within the same beam line. The other first for APS is what is known as a multi-bunch swap-out injection. Typically, all light sources operate in what is known as top-off mode, where we slowly dump inject beam at like a few nanocoulombs every few seconds or something like that. What APS pioneered is what is known as a swap out dump, in which if the charge in a bunch falls to like 90% of its original value, it's kicked out. So here you see the beam coming from the booster. That is, it joins the circulating beam. The bump that is the bunch that needs to be dumped is kicked out in the septum area into a swap out dump. So 90% of the electrons injected actually ends up in this swap out dump. By the way, top of injection also was pioneered at APS, which is now pretty common in almost all light sources. As far as the storage ring is concerned, sectors 1 to 35, where the beam lines are situated, has a wall thickness of 50 centimeters in what is known as the outboard side, that is this side. It's a high density concrete up to 7 feet and normal concrete beyond that. The roof is 1 meter thick and the radial or the ratchet wall is 80 centimeters thick. Sectors 36 to 40, this injection area, the concrete is 110 centimeters thick, normal concrete. And throughout the ring, it is 80 centimeters on the inboard side, which is towards the infield side. If you look at the insertion device, if you take one sector, for example, you can see there's an insertion device somewhere here. And the beam line comes out in this direction. There's a bending beam line which comes out in this direction and like that. So you have a bending magnet, an insertion device, a bending magnet, insertion device, and it goes on like that. If you look at the front end itself, which is this part, you can see that there are various components which they are circled in red and blue. So the red circled ones are those that can intercept the beam directly, the synchrotron radiation, that is. The synchrotron radiation is actually extremely powerful beam, although the energy is quite low. The beam power can be kilowatts, tens of kilowatts, in fact, depending on the insertion device itself. So there are the components that see the synchrotron radiation are undergo what is known as a finite element analysis for thermal stability and safety. The radiation safety components, which actually keeps the radiation levels low or water enters into the enclosures outside the storage ring wall, is those denoted by blue are protected by the components that are marked in red from the synchrotron radiation. So the synchrotron radiation never hits the blue colored components. This is like, for example, could be a lead, and of course lead will melt very quickly. Whereas these components like the fixed masks and photon shutters, they are all water cooled. And so is the safety shutters, which is made of tungsten. And once you enter the enclosure, there is exit mask, collimators, and things like that. And then if you look outside, so you can see that's what is known as a first optical enclosure, which is the enclosure right outside the storage ring wall, and that is where the major beamline components goes, like mirrors, DCMs, and things like that, typically. And then depending on the beamline, if it's an inline or a canted, you could have one or two arms coming out. And then, if the second enclosure is way downstream, there could be, in principle, be a section which is shielded beam transport. Depending on the insertion device, depending on if it's an insertion device or a bending magnet, the shield thicknesses are different. Almost all nominal enclosures are all made of lead in APS. This may or may not be true in other light sources. For example, in NSLS2, some of the downstream enclosures are made of steel. But there are some rules to the exception. Like, for example, in this case, this is a huge stainless steel tank. It's 40 meters long, about 3 meters in diameter. This is the end station right after the first optical enclosure. Oh, no, actually the second optical enclosure. And this is also the external station, but also as a shielding as well. So when deviations occur from the accepted procedures and policies. These requires a separate analysis, not just radiation shielding, but a complete analysis in terms of thermal radiation and things like that. The other safety aspect that I would like to mention is what is known as the accelerator safety, which is through what is known as a DOE order 420.2D. When supplemented with the other CFRs, it establishes that safe and healthy. It establishes a safety of the machine in terms for the protection of workers, public, and the environment. So essentially, the accelerator safety order says that you have to identify bounding conditions for your machine to operate, and then do the safety analysis based on that. So safety analysis is not just radiation safety, but also could be like oxygen deficiency hazard, electrical, and any other safety analysis that has got some amount of risk needs to be analyzed, documented, reviewed, approved, and if there is any change to that, it has to be reviewed again and reanalyzed if necessary. So the safety analysis actually feeds into what is known as an accelerator safety envelope, which is the bounding document that is approved by the DOE, and the machine is always supposed to be operated within that envelope. If it goes outside of the envelope, it's called an ACE violation. It's a very serious violation that could result in the machine being shut down. Will be asked to investigate, lessons learned, retraining, and re-reviews and things like that. The safety order also requires that an accelerator readiness review will be conducted in terms of, okay, the machine, people say, okay, we are ready to operate. We have all the people, processes, and equipment in place. So an external team will come and check whether what you're saying is true or not. So they'll check whether you have the people, process, and equipment, train people, enough people, things like that. Once the ACE has been approved by the DOE, the commissioning activities can start. So for example, in APS, for the APS, the bounding conditions are 126 watts of injected beam power for an energy of 5.5 to 6.3 GeV and a stored energy of 5,200 joules. Now, remember that this is the same electrons are circulating. So the current essentially is some amount of electrons, which can be converted into joules. And then once we identify the hazards and we have mitigated them using, for example, shield or whatever that may be, we have to ensure that that particular configuration is maintained. So we have a configuration management protocol. It's essentially to establish, document, and design the requirements of physical configuration, and there are various requirements within that. One is known as accredited controls, which I'll talk about in a minute. Essentially, they are engineering and administrative controls that are determined to be necessary for the safe operation of the machine. There are design requirements, like engineering drawings, work control requirements, which also I'll tell in a minute, change control, document control, and things like that. So if, let us say, through an analysis, we just determine that, there is a particular component that is necessary for reducing the radiation dose outside the shield, it's then considered to be what is known as a credited control. And every component, whether it's a shield block or a fixed mask or anything, has a sticker attached to it. It says that, okay, this is a radiation safety component. You should not be touching it. You should not be, you should not work on it. If somebody needs to work on it, they have to create what is known as a configuration control work permit, which gets routed, approved, and then they are then allowed to touch it, in the sense, open it and things like that, or move it. Once they finish the work, the component has to go back in its original state. It again gets reviewed and surveyed before closing out this work permit. And at that point, they're allowed to start either a beamline or the accelerator. So this is very seriously followed. If suppose a shield block in place is moved without a configuration work control permit, it's considered a serious violation that could result in the machine being again placed in a safe shutdown situation. So I mentioned about removal of the storage ring component. So obviously it requires some analysis as far as the activation potential and the residual dose concerned, because people are going to be working with it. There will be contractors, external people. So it needs to be identified what kind of doses are we talking about. Also, when we need to, it has to be transported, even if it is within internal within the site, there are certain protocols that needs to be followed. And if it has to be transported outside of the lab, then of course the Department of Transportation regulation comes into play. So quantification of residual nuclei in various components is required, and if it has to be free released, there is something called as ANSI, American National Standards Institute. It's ANSI screening levels are there, like which says, okay, the list of radionuclides are classified into 5 different groups, group 1 through 5, group 1 being the most stringent release criteria, which is 0.1 becquerel per gram. So the idea is to do a lot of analysis, mostly radiation transport calculations, and then ascertain the amount of a particular radionuclide, see which category they fall in, and develop radiation survey procedures, determine the MDLs for the detectors that we use, and then see if the components can be released or not based on the radiation survey that will be carried out. Quite often, for example, if it is a iron or steel-based component, you will have, let's say, iron 55, which is a major component, which is a low-energy photon-emitting nuclide, hard to detect through normal survey methods. So we rely on what is known as proxy radionuclides, which is, like for example, iron 55 is always accompanied by magnesium 54, which is longer lived and slightly higher. It's like what, 800 keV gamma emitting radionuclide. So by identifying the amount of magnesium 54 and by looking at the ratio between iron 55 and the magnesium 54, we can determine through to design through simulations using MCNP and calculating efficiencies and the MDLs for that. So that's one thing. So there are various components were analyzed for this purpose. I'll mention that in maybe a couple of them. So one is actually the old girder. So this is a Fluker geometry of the previous APS girder, and the components were modeled based on the information available. It's like 30-plus-year-old machine. There were a lot of information that was hard to come by. So, but anyway, so we managed what best we could do, and then we identified the radionuclides in the various parts of the component, the magnets, the yokes, the base plates, and things like that. And it was supposed to go into a landfill, but towards the end, all the girders were transported to the Brookhaven National Lab for use in their upcoming electron-ion collider project. So Brookhaven has the electron-ion collider actually is an electron heavy ion colliding beams, for which they already have the relativistic heavy ion collider in place. They have to build a new electron machine, and these girders apparently and the magnets and things were apparently perfect for them. So they just took it away from us. And again, since it has to be transported from Chicago to New York, it has to go through the DOT regulations. This is an undulator. It's again a Fluker geometry of the undulator with the composition of the magnets obtained from literature, and based on some accelerator physics estimations, we assume the beam that is getting lost in these what is known as a transition piece here. The transition piece here, and we determine the radionuclides that will be present in these kind of components. Similarly, the other components were like, the front-end components of a beamline. Some of the components were reused. Actually, most of it were reused, but some had to be discarded. There were a lot of lead collimators and then some lead shots, things that were not required had to be disposed of. So there was an extensive amount of radiation simulations carried out for that. Now, as far as a storage ring is concerned, we have to reanalyze the whole shielding for the new storage ring. So essentially, the way we do this here is to first identify beam loss points and the beam power of lost in those in the various locations through what is known as a forward particle tracking. This is carried out by the accelerator physicist, using the 3D field maps of all the magnets. That's about 1,300 magnets in the PSU machine. And they analyze this for two different scenarios. One is what is known as a normal operating scenario, which essentially is elastic and inelastic scattering of electrons with the residual gas molecules, and this what is known as a Touchek scattering and the injection losses. So similarly, for off-normal losses, this was done by studying the errors in the various magnets and power supplies and things like that. Now, of course, you can imagine that the number of combinations is so large, 1,300 magnets, and try to get combinations of a few magnets that actually can result in a particular accident. There's so many of them, but they found a way to do this, and essentially, as a result of the particle tracking, we have beam power, how much is getting lost in various sections of the storage ring, and based on, of course, the lifetime as well, injection efficiencies. And those numbers were used to normalize the radiation shielding calculation. So in a Monte Carlo simulation, you can start with one primary, but when you normalize the results to some beam current or total charge, we need to know what that is, and that is supplied by the particle tracking studies. So we identified the particle losses, the power losses from these kind of simulations. These are accelerator physics simulations. And then we determined for off-normal scenario, that is the injected beam getting lost, it's 96 watts. The results were normalized to 96 watts. But then we also have what is known as a beam emergency shut-off current monitor, which caps the total wattage at 12 watts on a rolling window of 1 hour. That's is further to reduce the dose rates, which in an hour that will be seen outside the storage ring. These simulations were also used to identify locations for new area radiation monitors. So the area radiation monitors in APS is mainly for stopping the beam in an accidental, if it gets into an accidental condition. So like, injected beam getting lost more than the, anticipated levels at the various sections. If the radiation levels go high, it trips the machine. We don't use it for, like protecting the people or workers. That's what some of the European organizations do. In which case, of course, we have roughly what 80-ish area radiation monitors, but that won't be sufficient because it's very hard to keep track of where the losses are going to happen from a radiation protection point of view. But it's not that difficult when you want is to trip the machine based on some accident scenarios. So the injection zone, of course, is where the maximum dose, the losses are going to happen. The septum and the swap out actually is sees the largest losses in pretty much in all machines. So there was already some shield in place, and we supplemented that using more shield, that can be moved, and this has to be closed. Again, these are, I remember about the sticker that I spoke about. These all have those stickers. So during maintenance time, they are allowed to open it, but when before starting the machine, it has to go locked in place and resurveyed and ensure that somebody walks around and makes sure that everything is in place as it was intended. In addition to the shield that is inside, we also had to put some shield outside, like a lot of concrete blocks were stacked outside of the outboard wall of the injection area. And then we have what is known as 4 horizontal collimators in the injection area, and essentially it's like scrapers which cuts off the beam if it veers too much off its course. So we have in addition to the shield that is outside of the storage ring wall, we also have some shield inside, specifically looking at losses from these horizontal collimators. So that's a CAD drawing, and that's installed the picture. So I talked about credited controls. So accelerator control interlock system, which essentially, all those search and secures, irradiation monitors, they all come under the ACES system. It's a credited system. Also, area radiation monitors, radiation shielding, the personal safety systems, all those fixed masts and collimators and the lead shieldings and the brimstone shielding in the beam lines and the ODH program, they are all credited controls. We also have what is known as an uncredited, we call it defense in depth controls. So for example, the BESOCM, the booster to storage beam shot of current monitor that I spoke about, it limits the average injected power to like 12 watts. One of the major concerns in any light source is, particularly when you are in a top off mode or in a support mode, is that the primary electron entering the front ends or the beamline enclosures is a very serious concern. Typically, beamline enclosures are not designed to take the full beam power, getting lost in some components in the enclosure itself. So we have to prevent these kind of incidents, as the beam is never supposed to enter anywhere in the front end or FOE. So to stop that kind of scenarios, there are a lot of interlocks, like the stored beam interlock. That means the beam will not be permitted unless there is stored beam in the storage ring. So when you start, obviously the safety shutters are closed. At that point, they are designed to take the full brunt of the whole radiation. But when the shutters are open, the shutters can be open only when there is all those interlocks are adhere to. So for example, the stored beam, there is also magnet dipole and the voltage of the dipoles. There are energy restrictions from the booster. The booster has not changed from the earlier 7 GeV machine to the current 6 GeV. So if we exceed 6.3 GeV, we are in violation of the ACE. So we have to ensure that the beam energy doesn't go beyond 6.3 GeV. There is an interlock for that. And then the various parameters, there's a software permissive, in the sense if it checks against a range of various parameters, like the voltages and things like that. And if it goes beyond that, the software itself can trip the machine. And then there's a beam trajectory limiting detectors. Operator training also is some kind of a defense in depth. So qualified subject matter experts are required to operate the machine. I'll come quickly to the beamline shielding part. So starting with the first radiation, which is a synchrotron radiation, here's an insertion device. It's a close-up of the magnets and the poles. So when the electrons wiggles through this magnets, you get synchrotron radiation. Depending on the energy of the electron and the magnetic field or the K value of an undulator, you tend to get various types of radiations. Typically, it will look like this. You have some peaks in from the undulators. And they are, like, you can see that the peaks can extend all the way to like 50-60 keV. This is specific. I mean, it's not specific to APS. It's any 6 GeV machine with this kind of beam current. This kind of undulators can, in principle, give rise to these kind of peaks. However, for all shielding calculations, these are like pretty much low energy. They are extremely high in intensity, but low in energy. But we use what is known as a Wigler approximation to calculate the synchrotron radiation spectrum. starting from all the way from 1 keV to 1 MeV. And for APS, we have to calculate up to 1 MeV because depending on certain shielding conditions, you could end up having 300, 400 keV photons dominating the dose. It's not much beyond 500 keV. Between 500 keV and 1 MeV, the change is not much, but between, like, say, if you consider only up to like 200 keV, and then the difference can be substantial enough to be noticeable, in certain shielding conditions. As far as the synchrotron sources are concerned, we have all these kind of undulators in place. You can see the critical energy here, which is as you go up, the 30 keV critical energy and this 26 one. These are superconducting undulators. The rest are all like planar undulators, which is the strongest one is like 3 centimeter period length and 3.3 centimeter period length. So the way the beamline shielding is done is we bound all the enclosures under one category of insertion device. It so happened that when we reanalyze the shielding for the new machine, we could not fit the entire shielding under this extreme superconducting undulators, but we managed to fit it under this envelope. So this is the bounding envelope as far as the beamline shielding is concerned. When they install these superconducting undulators, we'll have to reanalyze the shielding. Now, the other source, which is which comes along with the synchrotron radiation, is the gas bremsstrahlung. It is produced as a result of the circulating electrons interacting with the residual gas molecules. And the intensity depends on, of course, the straight section length. More the distance it travels, higher the intensity, the gas pressure and the composition, and the storage ring current. So for an APS, the ID straight section length is 7 meters. The bending magnet, because there are more magnets bending, and depending on the synchrotron radiation extracted from a particular bending magnet, the bending magnet straight section length is only 14 centimeters. So the GP power is in microwatts. It's, I think, like, if I remember right, it's like 40 microwatts for APS. The synchrotron beam power can be in kilowatts. So the difference is actually the GB is high energy, low power, and the synchrotron radiation is low energy, high power. Both are photons. For shielding calculations for the synchrotron radiation, we categorize them in various modes. Either it's white beam is that comes out straight out of the undulator. A pink beam is white beam reflected once from a mirror. And monochromatic beams, which is either white beam on a DCM, or that's how APS operates. It could also be a pink beam on a DCM. A DCM is a double crystal monochromator, simply using the Bragg's law of 2D sin n lambda is equal to 2D sin theta equation. So if it is white, monochromatic, the DCM can be placed downstream of either the white, that is undulator, or downstream of a mirror, that is for the pink beam. And depending on that, the intensity actually changes. The source strength can also be limited through apertures or limiting masks. And we look at scenarios for solid and gas scattering, like for a loss of vacuum condition, how much is a scattering from, let us say, 1 atmosphere pressure air inside a transport tube, for example. The mirror properties are also looked at. So the coating, reflecting angle, roughness also matters, but we don't take into account while doing shielding calculations. Typically, like 2 to 3 angstroms of roughness is present in most of the mirrors. Polarization of the beam, we have done both with and without polarization of the beam, and we use these codes that are shown here. So XOP is a beamline shielding, a beamline code which can pretty much model the whole beamline in XOP, including mirrors and DCMs. It's usually used by beamline scientists. I use it to calculate the source strength. So the plots that you saw before were all calculated using XOP code. Then I use StackHate for shielding calculations, as well as Fluka and FITS. IMD is another code that can be used to get the what is known as a reflectivity for a double multi-layer monochromator. I'll show that in a minute. So the source sum is calculated by using XOP. Reflectivity is through XOP and stack8 and IMDs. Bandwidth of monochromatic beams. I may have a slide showing that. Mirror roughness was calculated. The reflectivity of using for different roughnesses of mirror was calculated using XOP. Polarization can be taken into account by stack8 and Fluka, and then shielding calculation by using stack8, Fluka, and FITS. We also have what's known as a ray trace. So this is again unique to accelerators in the US. I've not seen this practice anywhere in Europe, at least not to my knowledge. So essentially, this is an AutoCAD drawing. I mean, essentially a screenshot of an AutoCAD drawing. What you have is the starting from the ID straight section, we propagate the beam synchrotron radiation from an envelope as defined by the vacuum chamber, and then we identify the components. These components are defined to the in the exact dimensions as they will be fabricated. So by drawing lines from various the sources, for example, the mirrors, we can identify if the beam will hit a component or not. So the idea is that the synchrotron radiation should not hit like for example, there's a shielded beam transport pipe. Should not hit. If it hits, it should be hitting only those the components that were circled in red in one of the slides before, which are the beamline components. It can take the heat load because they are water cooled and they have a separate personal protective systems in place. So by doing this, you can also we do this not only for synchrotron radiation but also for gas bremsstrahlung. Again, what is known as extremal rays are drawn to make sure to identify the nominal operating conditions as well as the missed conditions. And if we identify a missed condition, we reanalyze for that scenario. Depending on, let's say it's downstream of a mirror, things like that. Yeah, here is a slide to calculate the monochromatic bandwidth for a DCM, for example. It's done by XOP, but it's pretty much this equation that is given here. I won't get into the details, but typically bandwidths are the fundamental energy is like 0.1%, but the higher harmonics can, in principle, be calculated using this equation. We use in APS, we have there are ways, at least they have found some techniques in which they can get as high as 0.1% bandwidth for the fundamental using crystals that are asymmetric, imperfect, strained, or bent Laue crystals. So, and then there was some confusion about 0.1% applied across fundamental, not just fundamental, but across all the other harmonics. So that we had to sort of reanalyze the whole shielding based on the monochromatic beam bandwidths alone. Just to show a comparison between stack8, Fluka, and FITS results. So this is a synchrotron radiation scattering of a solid target, and in the downstream direction, this is the downstream wall of an enclosure. And if you look at the variation of the dose from in this direction, this is the horizontal view. You can see that both Fluka and stack8 and the FITS and Fluka pretty much agree with each other, but there is a small difference in stack8. And if you look at the cumulative dose, you can see that stack8 is roughly 2.5 times higher than what Fluka predicts. But if you look at the differential spectrum itself, you can see that there's a reasonable agreement, although there are a few locations where the agreement is not that great as well. But then stack8 is a very simplified code. It's very easy to run. So we always use that to get the upper bound of the shielding thicknesses. The mirror and source properties also matter, as I said. Like for example, in this case, the change of mirror angle reduces or increases the cutoff. You can see that's a sharp cutoff where the flux reduces, reflectivity reduces quite drastically. The coating material can also affect the reflectivity, and here is a mirror roughness. if you use this kind of spectrum here, and then we transport it across shield, you could in principle have like 200, 300 kV peak outside lead shields, but it could be even 500 kV, 600 kV if you're using thicker, let's say tungsten sheet, things like that. Here is a monochromatic beam. So a double multi-layer monochromator is something that is catching up quite fast. The advantage is that you can in principle get extremely high reflectivity for not just for energies that can be tuned based on the various bilayers, the thicknesses and the gap layers and things like that. There's no unfortunately, we have not found a way to sort of bound the reflectivity from a DMM, so it's done it on a case-by-case basis. As far as gas Bremsstrahlung coming out of the ID, we did this for like a few cases. Actually, we did for all the cases. So the insertion device beamlines are categorized as high heat load beamlines or canted beamlines. As I said, if you have two undulators at an angle, you get a canted beamline. But if they are inline, you get a high heat load beamline. So here is it's a complete geometry of the front end as well as the FOE and the various the downstream enclosures as well. And you can see that what's the dose rate that's good we expect outside the enclosure when the results are based on like 5 nanotorr pressure, because in the early days it was assumed that the EPS will have bad vacuum, so the pressure instead of 1 nanotorr, which is typical, was assumed to be 5 times worse. That brings to my my end of my talk. I have a couple of slides just for the youngsters in this group. As far as accelerated radiation production studies are concerned, these are my views. Something that I've seen over the years across 3 different continents. While I think there is no paradigm shift in the philosophy and practices of accelerated radiation production, it's because the underlying physics stays the same. There are techniques and regulations can vary, but there are gaps in the knowledge. For example, nuclear data and things like that. So as far as radiation production subject is concerned, radiation shielding, activation calculations, dosimetry, and radiation detection still rules the roost. There are some radiation damage studies thrown in for good measure. Attending some conferences over the years, I found that there's some great interest in space radiation production, cosmic ray radiation production, things like that. Is going to come up at some point or the other. So there is some scope there. There is quite a bit of mismatch between codes. Like, for example, when I started using FITS, I found that the calculations sometimes don't agree with what Fluka predicts. So there is some amount of nuclear data playing a role there. For example, Fluka uses the evaluated European nuclear data file, whereas FITS uses a Japanese evaluated nuclear data file. There is physics models for nuclear data integration with the radiation transport calculations can be interesting. I'm sorry, there is an extra integrating there. Radiation production in medical accelerators is catching up quite quickly. So accelerator medical physics and accelerator medical health physics both will have reasonably good scope. And then, of course, like everything else, we have artificial intelligence in radiation production as well. People are already working on it, and that is going to be the next big thing in the next I don't know, maybe a decade or so. So this is just my kind of quickly assembled wish list, so to speak. And with that, I'll stop. If there are any, and I'm ready to take questions.
Yeah, thank you very much, Dr. Sunil, for a very elaborate and comprehensive overview of the radiation protection in this advanced photon source, actually. And I request if anybody is having questions, they can start raising their hand in that app chat, or otherwise, Jayant, shall we open this for anybody can start asking directly, interacting with Dr. Sunil?
Yes, I think, sir, maybe directly people can discuss it.
Okay. So quickly, just to Dr. Sunil, one thing I found that a lot of Monte Carlo calculations have been uh, carried out in this exercise. I was really wondering about that computational time. How do you? Uh, that is the one part. It's we know how computationally expensive these Monte Carlo models and simulation. And then second is about the validation of the results when we have purely on model based. And also on personal dosimetry, I was little bit wondered how these high energy beams they have been handled. So these are the very general questions from my side, and maybe others also will have more questions. You can start answering. Thank you very much.
Yeah, sure. Let me start with your first question, which is the time taken for computational work. If you saw my acknowledgement slide, I thanked the Argonne clusters. We have an extensive and excellent cluster system here. We use that extensively. All my calculations are carried out in the Argonne clusters. For example, if you take one case where the GB for a beamline calculation, that is I don't know, let me see, 360 cores, that is CPUs over like 5 hours is one calculation. So that is just one scenario. So you can imagine, I mean, I've done probably like, I don't know, several hundreds of scenarios over the last few years. So it's expensive, but luckily I'm in an organization where there is tremendous computing power. We also have the supercomputer here now, which is the second fastest supercomputer in the world. I never even thought of looking at it because the clusters as of now is more than enough for me to get results in a few hours time. So that's one thing. I don't know if that answers your question.
Yes. Yeah, that's
The second one is validation. As far as validation is concerned, when we build a Monte Carlo model, it never reaches the exact configuration as in the as built condition. So there is always systematic errors. But if you're talking about validating the code itself, these kind of complex models are not the place to look for. These are essentially bounding condition kind of shielding calculations or activation calculations. If you were to do a validation study, you probably would do with a much simpler geometry and in a much more reproducible environment, like a beam hitting something directly and then computing the exact situation where you don't have to worry about systematic uncertainties and things like that. Having said that, we also have when we commission the machine, we also have what is known as shielding verification studies. So we cross-check the numbers in some fashion by dumping the electrons, the primary beam, onto various components. Like for example, the ID transition piece that I spoke about. It's very easy to dump the beam onto that region because the storage ring reduces in size to the smaller aperture ID vacuum chamber. So that we have done. And then there are such scenarios. As far as beamline shielding verification is concerned, it's we cross-check the numbers. When we do the shielding verification, we do these studies again, by putting scatter targets inside the enclosures and measuring the doses outside. it may or may not always agree, but at least in the accelerator case, we got some reasonably good agreement with the Monte Carlo simulation numbers. But that's because it's we managed to get the composition of the concrete, for example, characterized. We didn't know what was it at some point because it was built 30 years ago and there was no record of that. So all these factors come into play when we are trying to to do a comparative study. Like I said, if you really want to do a comparative study, you probably would do it with much simpler settings, with very low systematic uncertainties that could creep in. As far as personal dosimetry is concerned, we still use the same technique that pretty much everybody else uses. We have OSLs as our as a dosimeter. We take it from a company called Landauer, which is it's a leading company in this US here, probably around outside US also. And as far as the neutron dosimetry is concerned, the same company supplies CR39 based dosimeters. So it's a combined dosimeter of OSL plus CR39. We as far as the area radiation monitors are concerned, what we did is we characterized the response of the Anderson-Braun type REM counters versus the Wendy that we purchased recently, and then for various neutron spectra that could be present outside the shield, we characterized the responses of those, and we found that there could be a factor of 2 difference. But then we are not using it for protecting the workers. We are mainly using it to stop the beam from creating higher than per meter radiation levels. So a factor of 2 can be easily, even for personal dosimetry, a factor of 2 can be easily corrected. So
Okay, thank you.
So, Sunil,
yeah, go ahead.
So actually, when I was going through your presentation, I started asking some questions. I mean, started listing some questions. In fact, it went into 2-3 pages. I don't know whether Dr. Anand will permit me to ask or not. So what I will do, I will just take up some few important questions. So the remaining probably we can communicate later on, because other people also may have some queries and all those things. So my the first question is that, because rather than asking all the questions together, I will take one by one so that you can quickly answer. I know that you will be able to answer very well. See, because that we have a program of 6 GB machine at Indus.
I don't know that. Sorry.
Yeah, we are going for, of course, there is in the preliminary stage, the physics design is already going on. And probably the CDR is being written. And we do not know whether the government will approve or not, because a huge amount of money is involved in that, and the user, what is the user demand and all those things. How do we convince them? Anyway, we are going ahead with that project. So in connection with that, I have one question, that the central well area, which you have shown where the LINAC and booster is there. You have the ring, and inside the tunnel, I mean, in the what you call the central well where the LINAC 450 to 500 MeV LINAC and the booster is there. So what is the accessibility to that area? Is it a prohibited area, or is it a controlled access area?
So quite a lot of it actually is accessible to APS personnel. I mean, it may or may not be necessarily open to personnel outside the APS, even including for the including people who are in Oregon. So but then there are a lot of areas that are actually sort of fenced off, because, and the photograph doesn't do much justice to the actual configuration. The booster is actually under a berm, so there is quite a lot of earth acting as shield. So is the LINAC. LINAC actually there's quite a bit of earth in addition to the concrete walls. So those areas are actually off limits. It's all fenced off. Nobody can go there unless HP permits. It's under lock and key. So where we expect radiation levels to be high, it's kept under lock and key.
Yeah, so it is a restricted access. I mean, in case requirement is there, one can go that. So regarding
at that point, we need a HP permission, and HP has to be notified. They have to come and open the gate for them by surveying before they enter.
So the LINAC, you have a different control room, or it's the same control room where the storage ring and booster and everything is controlled from a single control room?
Yes, there's one control room.
Right. So now, as far as these users are concerned, see, are they treated as radiation workers or common public?
So that's an interesting question. Why? Because the previous APS was free for all. I mean, you could walk into the experimental area and then without a dosimeters, for example. For the new machine, when we were analyzing the shielding, we said, like we gave them an option of, shielding that to 0.05 milliamp per hour, which would have allowed us to let the users go in without a dosimeter requirement. But then it didn't materialize. We went through for what is known as a 0.5 milliamp per hour, which is the 10 CFR 835 limit. That's the legal limit that we have to adhere to. The 0.05 would have been a much better number, but so when we decided to go with 0.5, we insisted that every single user who enters that access control door into the experimental floor will be monitored, and they will be issued a dosimeter. They will also have to undergo what is known as training. There are different types of training. For example, there's something called GERT, General Employee Radiation Training. There's a Radiation Worker 1, Radiation Worker 2 kind of trainings. If the trainings, so they have to undergo that basic training and be issued dosimeters. This is going to be like that for at least 5 years. So in that period of time, in the early days, we don't know how the APSU is going to operate because it's pretty much first of its kind, even though it is an MBA lattice, because it has got the reverse bends, it has got the support injection, things like that. And then of course in the early days the vacuum could be pretty bad. So we decided, okay, we will have to monitor every single person entering the APS. That's about a few thousands of dosimeters in a year. The APS gets about like what 5,000 users or something like that. So there's a lot of users coming in. And then we are going to monitor that for next 5 years. We have a lot of passive area radiation monitors, like the dosimeters placed at various locations. So we look at the data and then we analyze after a few years and then see if any of those. We look at the data of the users. At some point, we'll make a decision whether we can let people in without dosimeter or not. My gut feeling is that it's going to be possible in maybe like a couple of years' time. We need that much data to convince not just ourselves, but also the DOE folks. So
yeah, actually, this is a good method, but in fact, and I was trying to compare the synchrotron facilities and how they look at the users, whether they are treating as radiation workers. So, see, I found that most of the facilities except Japan, Spring 8. So the Spring 8, they consider as radiation workers. But if you go to Electra, sorry, not Electra, what is it?
ESRF.
ESRF and all those, they treat as common use, I mean, public, so that actually they wanted to encourage users because they will be coming for 2 or 3 days, and if you put a lot of restrictions and all those things, then there will be a reluctance for people to come. So this is what one feeling, and you have to have deploy a large amount of radiation monitors for the users, which will have to be read and all those things. So it becomes a problem. So here what methodology we have adopted is that we, of course, we treat them as radiation workers, but much more than that, we strengthen the radiation safety training. We are asking people to sit for a 30 minutes audio-visual training module, which tells about the radiation safety systems, etc. And also an examination, an online examination we are conducting with 80% pass mark, and allow them and strengthen the interlock system so that we prevent people from getting accidental exposure. This is what we follow. So anyway, it is good that you are highlighted what you are going to do there. And another is that regarding the beam loss scenario, because all the radiation protection measures are basically depending on the beam loss scenario, what is happening. So what is the typical injection efficiency which you take for the calculation from the, for example, from booster to storage ring or LINAC to booster?
So as far as I'll speak about the booster to the storage ring. So right now we are well above 95%. I think it's like we are somewhere at 95, or I think it's above 95%. So the aim is, I think, like 98% or something like that. So we will be reaching there very soon. Now, as far as the shielding calculation is concerned, we took the 10th percentile of the entire loss scenarios actually based on the worst lifetime. That was like what, 2.8 hours or something. So it was a combination of I mean, if you're talking about the normal loss scenarios, it is based on
But
the
this
lifetime.
the I'm talking about the normal loss, but this
Yeah.
storage ring will be in the top up mode, no?
The storaging is in swap out mode. It's top off is we don't use top off anymore. I mean, we introduced the swap out. It's the first time it was introduced in the world. So like 90% when the charge in a bunch falls to 90% of its original value, it's kicked out, and in the same RF bucket you put in a new bunch from the booster.
Okay. So it is, you can say that semi top up, you can say.
Yeah. Well, okay. I mean, it's yeah. Top off is actually you don't throw away the charge. You simply keep adding on top of it into the bucket, so to speak.
Okay, so maybe we will discuss
But
more.
if I remember right, I mean, okay, if you want to know the exact injection efficiency that was used in the calculation, I can look up. I don't recall that exactly now.
Because many of these informations are not available in the literature and all. In fact, I was about to communicate to you, but since this program is being picked up. So anyway, we will. But another one important thing which I wanted to ask is that the use of lead in the beam lights. So, I mean, you have in one of these slides which you have shown that lead shielding is provided for, even in fact for the mass collimators, etc. But does it not produce additional neutrons? Because this.
Yes, it is true. It produces neutrons for sure, but with microwatts of power, it's manageable. That's a difference. The reason why there is all those lead is there in the beamline is because I talked about the ray trace, so the early years of the light sources in the US, they all relied on ray tracing because there was no good way of doing a Monte Carlo simulation at that time. Like 1996, if you were asked to do a Monte Carlo simulation, you probably I don't know how many of us could have done that at that point in time. There were not enough computing power, things like that. So they relied on, analytical methods, and one such method is a ray trace. So when you draw a gas Bremsstrahlung with an exaggerated size of gas Bremsstrahlung, instead of your 80 microradian divergence, if you blow that up much more, and then start drawing lines through the fixed masks and the other optical components, you end up with GB rays hitting a component, going through some. The idea was to stop the GB ray in wherever it you can draw a line. So it's not a foolproof method in the sense, they assume that, for example, that GB ray will do nothing when it goes through the copper mask, but will get stopped immediately at the lead. So there were a lot of shortcomings in the method, but that's what we ended up with. In principle, it can be it may be possible to remove it, but that requires a full-fledged analysis.
Yeah.
APSU was like a project with a deadline, right? So there was no time for us to do any R&Ds. So changing the configuration of the beamline was immediately ruled out.
So one possibility is that some additional HDP can be provided so that whatever additional neutrons are provided can be stopped. So that is one possibility.
So in some beam lines where we do find neutrons, particularly, the first optic enclosure, I don't know what you call in your place.
You also
but
call the same thing, yes.
Okay, so the first optic enclosure, the first component in the FOE is actually the exit mask, and sometimes it is followed by an exit collimator, which is lead. The exit mask is where you get the bulk of the neutron production, and it goes in the lateral direction much more than, because it is a shorter distance. So we actually we locally shielded that with polyethylene and things like that.
Yeah. So another one more very important question which I wanted to ask is that, do you consider the channeling of electrons into the beam lines? See, for example, in the case of an undulator beam line where you have tens of meters or maybe up to 10 meters of straight section, and if all of a sudden if the beam loss take place, can there be a possibility of channeling these high energy electrons of 6 GeV into the beam line? And if it takes place, how do you take into account? Have you done that analysis sometime?
Yes,
This is an accidental case. This is an accidental case.
I do have a slide. I didn't show that. I mean, I have that in the same presentation, but I mean, there were too many slides at some point. I had to cut it down. But this is all, of course, always a major concern in any light source. Like when the safety shutter, the front end safety shutters are open, and if you are injecting beam in a top off mode or in a swap out mode, there is always this fear that the injected electrons could in principle end up in a phase space that is somewhere in the vicinity of the front end of a beam line. There were quite a lot of simulations were done, and essentially the way we have radiation monitors in place to trip if such things happens, because the radiation levels are extremely high, like 800 millirem, 1 rem kind of dose. But this is the assurance is that if such a thing happens, the machine people will realize it as quickly as possible, and that is one our defense on that. The second one is I talked about the particle tracking studies, and this is done in an extensive manner. I mean, this quite laborious, and it's tremendous amount of calculations that gone into those kind of analysis, and it's pretty much identified. Look, there are a couple of magnets, like there is one transverse dipole magnet that if its power supply error exceeds a certain number, there could be a possibility of electrons entering the front end of the beam line, not the FOE. FOE is further downstream. So that fear is there, and then but we did a lot of Monte Carlo simulations for electrons hitting, let's say, the exit mask in the FOE, or the front end mask and things like that. But then people thought of putting like what is known as a clearing magnet. Like if you have an electron entering the front end, if you put a strong a magnet, it could actually deflect the electrons onto some kind of a safe location. So these things were looked at. And again, if the electrons are getting lost in the front end, the storage ring is reasonably thick enough to reduce the dose rates. It's the FOE thickness that was going to be problematic if you have beam entering the FOE, and that would be a serious consequence. But in the end, we decided that, okay, we have enough systems in place, like all those interlocks, the defense and depth interlocks that I talked about, the dipole voltage interlock, the stored beam current. So we won't allow the safety shutters to be opened unless there is a certain amount of stored beam already in the storage ring. That precludes any magnet errors, and then we check at the dipole voltage and the dipole current to make sure that all the dipoles are operating.
Essentially, the reliability of the system has to be so high that such type of events, we should prevent from occurring. So
yeah, and then also don't forget that we have got the software permissives, which actually keep a watch on the range of the parameters, right? So if it goes beyond the range, it triggers a beam dump or a beam inhibition.
Yeah.
Yeah, Dr. Haridas Salvi asks if others are having some question.
In
Again,
fact,
we will come back
yeah.
actually. Yeah.
In fact,
Hari,
I was
I will
about
send you an email. You can ask as many questions as you want.
I was about to stop here because I know that Dr. Anand is going to arrest me.
No,
So,
no. We will see any other participant
yeah,
has question.
definitely, I would also like to thank Dr. Sunil for giving us such a very wonderful presentation. And of course, there are a lot of challenges involved in that. I know because I have been in this field for many years, and Sunil has wonderfully handled that. And anyway, probably Sunil, we may have some interaction through email and all those things.
Absolutely,
Okay,
no problem.
Anant, you can.
Yeah.
Thank you so much.
Yeah.
Sure.
Jayant, are any participant has yeah, please. I think Dr. Sarkar is Dr. DN Sharma also joined, but nice to see. And Dr. Didi Rao is there. Please, someone has question. Yeah, please. Hello, sir.
Hello, Dr. Anand. I am Didi Rao.
Yeah, yes, sir. Yes, sir. Please go
So I
ahead.
just came to. Actually, I saw the message today only in the after 10 o'clock. So I joined late. Anyway, I want to congratulate Dr. Sunil, and he's in ANL. I was not knowing. A few months back, actually, Dr. MRI was asking me to contact Sunil for some help and all in publications. But anyway, I was not having address. However, I joined now just to congratulate Dr. Sunil. Anyway,
Sure.
this topic is also not related to me, so I joined late. So congratulations, Sunil.
Thank you. How are you?
I'm fine. I'm fine. I'm at Hyderabad now.
Oh,
So
good.
hearty congratulations.
Thank you. Thank you.
Just around 10 o'clock, I saw the WhatsApp message that your program is there. You are in India or there?
No, I'm in the Chicago suburbs.
Okay.
Dr.
So
See, yes, sir. You have any question? Otherwise, Dr.
no,
Bakshi.
nothing. We will. You and myself will contact him in mail.
Yeah. Sure, sir. I think Dr.
Okay.
Bakshi has some
Yeah,
question. Yeah, please go ahead.
actually, Sunil is a nice presentation. Actually, I was enjoying. But the questions which are related to, again, personal monitoring, we always face a question like in accidental scenario, if a person is maybe trapped in the hutch area. So how do you do the calculation for the estimation of the personal dose? Because the personal dosimeters are not designed for such a high energy as well as low energy. So that is one point. Another is outside the shielding, if you have a 6 GeV machine, what will be the photon spectrum for which this lander dosimeter will be able to measure the dose effectively?
So, yeah, I mean, this, I think we have been having these discussions for, I don't know, for as long as I can remember. So, if you are talking about the beamline enclosures, it's, the gas Bremsstrahlung induced radiations are there, but again, it's quite low. We don't expect people to be trapped inside the enclosure. There are a lot of safety features that prevents that such a scenario. So in the beamline enclosure, if somebody gets trapped, actually it's a very serious problem for us. We in all probability will have to shut down the machine, undergo a lot of reviews and things like that. So we do this through like a lot of training. The users are trained. Every beamline has got their own training in terms of which door to open, which button to press, things like that. So if you are a user in a particular beamline, they will have their own trainings that you will have to take to make sure that you understand how to operate it. The user is not expected to go into the first optic enclosure. They usually have the experimental stations are the second or the third ones, and by the time the beam is there is no gas Bremsstrahlung induced beam in that things because it's pretty much it's a DCM based beam, that means that a double crystal monochromator has already intercepted the gas Bremsstrahlung part. Nothing goes beyond the white beam transport region. Again, the same logic applies for people in the tunnel. I mean, we do not expect people to get trapped inside the tunnel. There is a search and secure team that goes around securing areas, just like any other machine. And then we have all those alarms, the scram buttons and things like that. So, but outside the shield, we have done some simulations, and there is some gap in that process there. I admit that, and I'm actually working towards correcting it. So the simulations might show like up to like I think about 100 MeV of photons, although the fact it's reduced by like several orders of magnitude compared to, let's say, 3 MeV photons. But there is some small gap there, which is well known to pretty much all the light sources, particularly the high energy light sources.
Have you even measured the energy of the photons or the neutrons which are coming outside the shielding?
No. So the APSU was just started like a few months ago. So right now the machine is commissioning. We didn't have the chance to measure anything. I mean, we had to quickly rush through the shielding verification studies to get the machine operational. No. So the answer is no. Yeah.
Thank you.
Sure.
Okay. I think if any other question, can wait for a minute. Otherwise, I will request Mr. Jayant. I think Tripati, you have something to ask?
Yeah, I wanted to ask something.
Yeah. Please go ahead.
Just curious to know that what kind of personal dosimetry for pose they are using, for the neutrons. What kind of dosimeters they are using?
For neutrons, we use a CR39 based dosimeter. Again, it's from a third party. We don't have anything of ourselves. We outsource it to Landor.
But that will not cover the entire energy, I think, no?
Yeah, sure. Yes. There
Okay.
is, as I said, there are the same gaps that existed.
Yeah. Okay. So
50
is there
years
any
ago,
spectrometer, neutron spectrometry, how this is being carried out?
we don't have any
Spectrometers
provisions yet to carry out any neutron spectrometry work.
Okay. Yeah. Fine. Acha, I think Dr. Sarkar also there. You would like to say? Otherwise, I will request Mr. Jayant. You can. Yeah. You can go ahead with vote of thanks. And anyway, it will be very late. Maybe 11. Maybe Sunil, Dr. Sunil. Yeah, it may be night.
Yeah, it's close to
11
midnight.
o'clock. Yeah. Anyway, thank you. And anyway, formal vote of thanks will be given by Mr. Jain. Please go ahead. Yeah,
Thank you, sir. Thank you so much for the nice presentation. So, good morning, everyone. Now, on behalf of IARP, I would like to extend a heartfelt gratitude to Dr. Sunil for such a comprehensive and insightful presentation on radiation protection during the upgrade of advanced photon source. We really appreciate your time and efforts for sharing your knowledge and expertise with us. We are sure that discussion will definitely give a direction and spark up more ideas to the professionals in the early phase of their career and peers working in the field. I would also like to thank IARP for providing this opportunity and a platform for bridging the gap between the professionals and the experts, and where we can come together for discussion. And every month we are meeting for new lectures and ideas. So I would like to thank IARP for providing that platform. Also, I would like to thank the attendees for participation, their active participation and attention. Thank you all for your valuable contribution in every aspect. Have a great day. Thank you so much, sir.
Okay. Bye-bye.
Yeah. Thanks, sir.
thank you. Bye. Thank you.
Dr. Anand?
Yeah.
Is there any tea session after this?